All right, so, well, there is stuff that we need to do. Actually, it's kind of overdue, is the area and the circumference of a circle. It's going to be very, very important. Circles, not their equations, which was the extra credit assignment, but just areas and perimeter. But instead of perimeter, we say circumference. So the area of a circle with radius r is pi times r times r. And the circumference is 2 times pi times r. Now, what attracted me to mathematics is that I hate memorizing. I hate it then, I still hate it. And so it was a little disturbing for me that they were a little too similar for my taste, the two formulas. And the way I remembered is that both formulas have the same three characters. There is a 2, there is an r, and there is a pi. But if you look at and think of units like feet or inch or mass or meters, one of them is obviously a length, while the other one is obviously an area, as in a length times a length. Can you see why this one is obviously an area and not a length? Because r times r, that's feet times feet, right? Pi is just a number. It's just too hideous to use the 3.14 and the gazillion digits. So basically, both formulas have the same characters, but one of them is a length, namely the second one, and the other one is an area. So that's what worked for me. So what do you think the area of this semicircle will be compared to the area of the whole thing?
It would just be half of the
Exactly.
circle.
And this is called an arc length. This is called an arc, and the length of the arc is, surprise, surprise, it's going to be half of the circumference of the full circle, right? But it's not just half, but quarter or 1/10 or 1/9 or whatever. So there are going to be two very basic questions asked of you, namely that find the area of a sector of 43 degrees in a circle with radius 7 inches. Now, I know you can do this, but I just want to show you a really quick way, because it's just a matter of ratio problems, but you do not have the time to set up an unknown and draw a little table or whatever. You need to speed up that ratio problem. So let me show you how I do it. Well, let's start with the full area. Full circles area, which I'm not even going to bother with the numbers, is pi r squared, right? And then I'm going to say, let's take a sector. Imagine that we have a gigantic pizza, really, really big. And then we need to cut it into a lot of pieces. So we cut it into 1 degree slices, like a really, really thin. But, you know, if the pizza is big enough, that's going to give you something to chew on. So second step is the area of 1 degree sector. Can you make a wild guess how that's going to relate to the full area? 1 degree.
Would it be divided by 360?
Yeah, it would. It would be. If we cut it into 2 parts, then divide by 2. If we cut it into 360 parts, then it's divide by 360. And now take 43 servings of that pizza. I call it scale it down and scale it back up. So take, because it's 43 degrees, 43 servings of this. It's pretty reasonable. So it's going to be pi r squared over 360 times alpha, but you don't have to memorize it. Just remember the story. Or in this case, pi times 7 inches squared divided by 360 times 43. And the degree cancel out, but it just looks so goofy if I write degree and degree, but they actually cancel out. That's it. I think that's the simplest way to do it. And then we just punch in 49 times 43 divided by 360 equals, and we multiply it by pi. There is a pi button. The problems that I wrote will say use the pi button. Don't enter 3.14. this is the buy button gives you a much better precision. And so it's 18.387, whatever. Square inches. And in physics, it's kind of interesting. In physics, you go nice numbers, ugly numbers, units. So in physics, this is a particularly disgusting example because 49 times 43 has nothing to do with, so it would be 2107 over 360, welcome, many pi square inches. So nice numbers, yeah, at this point, this goes by nice, ugly numbers, units. That would be the exact value. This is the approximation. But the point is the ratio problem. And then guess what? I can ask the same thing about the arc length. It's just the language is insane. I don't know why. It goes like this. Find the length of the arc subtended. Don't ask me what that means. I have no idea. Subtended by a central angle of 43 degrees in a 7-inch radius circle. So it's the same question, but instead of area, now it's arc length. But somehow the language makes it sound so differently in a 7-inch radius circle. So if I may just start with the full circumference, then take a 1-degree slice, and then take 43 servings of it. That's just a very quick and dirty way to do it. See, and this is going to be a length, not an area. Now, at least there is something that this is like exact value. I canceled out this 2. That's the only thing that can get canceled out. These are terrible numbers I picked. So it's 301 over 180 pi inches. Welcome to physics. Nice numbers, ugly numbers, units. That's the exact value. And then the approximation, oh well, times pi divided by 180. Okay. To show you an example of the kind of sort of things you can expect, let's start with an easy one. Now this is a circle in a semicircle, and let's say that this here is 4 meters, and find the shaded area. And if the problem doesn't say exact value or approximation, just get both.
Isn't 4 the rate? I don't know. I think 4 is the radius.
Well, there are 2 circles here.
Oh.
4 is the radius of the semicircle. You're going to be the one who has to figure out the radius of the smaller circle.
So isn't the radius of the smaller circle half of the radius of the larger circle?
Exactly, because this is still 4 here, right? It's the same radius. And then you take, that's a diameter, so this radius is 2 meters. So that's going to be part of the deal. You have to figure out certain connections based on the picture. Very good. And now it's just find the area of the semicircle, find the area of the circle, and subtract and keep your cool. And you shouldn't get a negative number. So it's not that bad, but just these kind of connections you have to read from the picture. You're probably getting used to that stuff by now. So it's going to be the area of the semicircle minus the area of the full circle. And I think it's exactly half. You will see, we're going to keep it abstract for a while. So the area of the semicircle is 1/2 pi times 16 square meters, right? Pi r squared. I just did the r squared. I'll be nicer, but yeah, I think it's going to be something like that. By r squared minus the full circle, full, I said pi times little r. You see, I'm using little r for the smaller circle and capital R. That way I don't have to, I don't know. Just something I get used to it. So that's 1/2 times pi times 4 meters squared minus pi times 2 meter squared. So that's 4 squared is 16, but there is a half here, so it's 8 pi square meters minus 4 pi square meters. You see that this is half of that. So it's kind of interesting. If you look back, I found that surprising that the shaded area is exactly half of, maybe it's not such a surprise, but I found that like, wow, at least visually it was surprising to me. So what we have is just 4 pi, right? 8 minus 4 is 4. That's the exact value, and the approximate value is 12.56637. Okay, that went well. Any questions? Do you happen to know the radius of the Earth?
The phone says 3,963 miles.
Thank you. 39, it's 59 and 58.8, but who's counting? This is good enough. Okay, you need that, and every time you need that, it will be given to you. So here it is. Here it is how it's going. A satellite can be seen over the equator as if it was standing. I mean, by standing, I don't mean it has feet. It means it's stationary. It's not, it appears when we look up, it appears like it's not moving. So we're somewhere at the equator, we look up, it's not moving. If the satellite is 800 miles above the surface, how fast is it really moving? Well, why is it moving if it appears stationary? I know I said it's moving, not you, but I'm asking you, do you have any idea why would it be moving if it appears stationary?
Is it because the Earth's rotating?
Exactly. We're not stationary, so if they appear stationary, they're moving together with us. So exactly. So it's basically going to follow exactly the rotation of the surface of the Earth, which is what? One full rotation in 24 hours, right? Yeah. So the velocity, which you should know, is the distance traveled divided by the time. You know that, right? I hope you're not going to lose points and stuff like this. Well, now you know. And so we can say that in 24 hours, it goes around the full cycle. Well, you know, we can assume that's a circle. We can assume the Earth is a sphere. It's not quite, but almost. So how can we find? I know I shouldn't draw that picture for you because it helps. So the orbit of the satellite is, we can assume it's a circle. What's its radius? I'll give you a hint. It's not that. I'm not sure I'm happy with my picture. One thing you can do to make it more three-dimensional is the stuff that's supposed to be visible, you make it darker, and then it kind of pops out from the picture. This here is the Earth's radius. So what's the radius of the orbit of the satellite? Look at the picture.
Is it? Yeah,
It's
right.
Right, it's the radius plus that 800 miles or whatever the height. You see, that's the radius. I don't think I helped. So basically, the radius of the orbit is, well, r plus h, or 3,960 miles plus 800 miles. No, I don't think it's a really difficult one. It's just kind of intimidating. I'm gonna do it. 3,960 plus 800 is 4,760 miles. So that's cool because we get the answer is miles per hour, which is not that insane of a unit. And that's it. We're just punching the rest. So that is the 4,760 times pi divided by 12. I canceled out between 2 and 24. And is 1246. Be prepared to have to, I think in this problem, I make you round to the nearest integer. So it would be 1246 miles per hour when you do it in online. That's pretty fast. That's like 10 times speed that is already dangerous. So that's pretty fast for appearing stationary. Okay. Any questions? So I thought I'll show you, this is a really cool problem. This was a contest problem for 2-year colleges. It's number 13. Can you read it?
Yes.
No, well, because I made it go away. I was trying to resize the. Suppose that the Earth is a perfect sphere, and then we make a belt on it. Kind of funny of an image. And the belt was cut perfect, and then 100 additional feet was added to the belt. Maybe the Earth is planning to gain some weight. With the loose feet evenly distributed around the Earth, so that the new belt was still circular with its center at the center of the Earth. Which of the following? So basically, we made the belt 100 feet longer. That's what it says. And so, you know, if you make a belt longer, then you can pull it out a little bit. So the question is, how much is it away from the Earth's surface? You could slip a piece of paper between the belt and the Earth. You could get your fingers under the belt. You could crawl under the belt. You could walk upright under the belt, or you could drive a truck under the belt. You know, just have your instinct with you, because my instinct just royally failed on this problem. Maybe that's why I remember it so vividly. Which one do you think is going to be true? So just make a wild guess, A or B or C or D or E.
I think
As
A.
You think A. So closest to it, it comes that you could, because obviously if E is true, you could still slip a piece of paper between the belt and the Earth. But yeah, that was my guess too. And it's off, because the Earth is so big compared to that 100 feet. So it feels like that wouldn't make much of a difference. But well, let's just see how that works. Actually, the truth is the last one. You can drive a truck under it. That's pretty crazy. So I don't know if that 24,000 is necessary. Let's see. So the belt is 2 pi r, which the problem claims it's 24,000 miles. Maybe it's rounding, maybe it's, I don't know, plus 100 feet, right? That's the length of the belt. Here is the perfectly fitting belt, and then we added 100 feet to it. Now, what happened is that the belt is a little bit away, just like the previous picture. So we need to find this difference here. So what's the new radius? And when we subtract the two, the new radius and the old radius, that's distance. Is that a truckload or just a piece of paper or anything in between? What's going on? The circle got a little bigger. What's the new radius? 2 pi r new is 2 pi r plus 100 feet, right? And we want to solve for this, right? So we had the circle, and then we added 100 feet, and that made a bigger circle, and we want to find the radius. And so radius of the new one is 2 pi r plus 100 feet divided by 2 pi. So that's r plus 100 feet over 2 pi. Right? This is the basically 0, the new radius, the old radius was r, right? When it's right on the surface. Now, and so 100 feet divided by 2 pi, you know, pi is 3 and change, 2 pi is 6 and change. So 100 divided by 2 pi is actually 16 feet, almost 16 feet. Now, I'm not that good with feet, but I hear that you can drive a truck under that. Yeah, that's like 3 persons, 3 average sized person standing on top of each other, right? That was pretty surprising to me. Because basically this computation shows that it doesn't matter how big was the circle. You add 100 feet, the radius will go up by this 15 and change. Isn't that weird? All right. Now there are two more applications I want to show you, but we'll probably have time for only one. So let me start with one that I like. It's basically, let's assume that this is a unit square, find a shaded area. So before we do this problem, let me just point out something that became sort of accessible now that we have this stuff and right triangle trigonometry. If I ask you, so I give you, let's say the radius is 6 meters. And let's say that this angle here is 28 degrees. I can ask you now to find this area. Because I don't even know how you call this little section. It's like the top was sliced off, but this is a sector minus a triangle. You see, the whole sector is just a ratio problem. You take the area of the full circle, you divide by 360 and then multiply back by 28, and that's that. On the other hand, we have an isosceles triangle where we know the two sides, 6 meter and 6 meter, and we know this angle to be 28 degrees. So with this newly found, well, you could sweat, and with right triangle trigonometry, you can find everything. This is really small. This is 6, and this angle is 28 degrees. So you can find the area of this triangle. Now, you could do it right after right triangle trigonometry, but now it's really easy with that new sine formula. The triangle's area is 6 squared, 1/2 times 6 times 6 times sine 28. There, done. And then the sector is going to be pi r squared over 360 times 28. It's interesting because these are algebraically completely unreconcilable. This one has 28 degrees alone. This one has inside a sine. That's kind of a, you cannot simplify it. You can just get an approximate value, but you can always find these kind of weird things now that we know right triangle trigonometry and these ratio problems with circles. Did you draw the picture? Because if you can draw it, you already understand a whole lot of things about it. Make a good picture. There's just a few things noticed, and one of them is a semicircle. You see a semicircle there? Actually, 4 of them. So this is a semicircle, and so is this, and so is this, and so is this. Right? So that's how the picture was generated. That's the first thing to observe. And then I think there are lots of ways to approach it. Clearly, we know the square's area is 1. So if we can find the total white area, then we can find a total shaded area because we just subtract it from 1. And sometimes the white area is easier. In fact, I think, yeah, this is what I would do. But it takes a little getting used to. Check this out. I think this here is exactly what I described. I think this here, just this half of this white thing, is a sector minus a triangle. Of course, you have to draw in this. You see it now? So let's just find this incy little pink area. How long is this side here?
It's 1/2.
Yes. how long, and so is the vertical, right? So it's 1/2, and this is a quarter of a circle, and the circle's radius is 1/2, right? And it's exactly a quarter. So the sector is pi times 1/2 squared divided by 4, right? This is the area of the full circle with radius 1/2, but we just need a quarter of it. And from that, we subtract this triangle here. Now, this is an isosceles right triangle with the shorter sides being 1/2 and 1/2, right? What's the area? You don't have to compute it. Just tell me what to write. Tell me apply a formula. You don't have to compute it.
It's 1/2 squared, or 1/2 times
1/2 squared.
and
Exactly.
then multiply it by
That's
sine.
it.
Oh, okay.
No, you're
that's
done.
it? Oh, because
That's it.
you already have the base and height. Oh, okay, I see. Yeah,
Right,
yeah.
one side is the base, the other, that's what right triangles do. So it's 1/8. And so this little fuchsia thing is the difference, which let's hope, let's keep our fingers crossed and hope that it is going to be positive, because this one is pi over 16. You see 4 and 4, so this is pi over 16, and pi is more than 2. 2 over 16 would be 1/8. Pi is more than 2, so we're in good shape. So the area of that little, I don't even know how that called, that little slice, is the difference between pi over 16 and 1/8. And then if we want to find a wide thing, we have 1, 2, 3, 4, 5, 6, 7, 8 of them, right? So 8, the area of 8 times that slice. Oh, that's interesting. It's 8 times this here. Pi over 16 minus, let's just make sure that pi over 16 minus 1/8 is positive. I think it is, but pi over 16 minus 1/8, it's positive, but boy, it's not big, 0.07. But I'm just finding it interesting that we multiply it by 8, so pi over 2 minus 1, interesting. Now, you know, pi is 3 and change, so pi over 2 is 1.5 and change. Well, I can still multiply it by 8. So I had still that slicey, I just multiplied it by 8. And for the shaded area, we subtract that from the 1. So for the area shaded is 1 minus the 8 times the area of the slice. So that's 1 minus 0.57079. You know what? I actually want to do this. It's 1 minus pi over 2 minus 1, which is 1 minus pi over 2 plus 1. So that's 2 minus pi over 2. That's cool. Pi over 2 indeed is bigger than 1, but less than 2. So yeah, I like that more. But either way, 2 minus pi over 2, 0.43, something like that. So cute problem, just don't let the picture intimidate you. Most of them are boiled down to, this is the worst case scenario when you have a sector and a triangle. In fact, that reminded me of another cool problem. I'm just not sure I can find it quickly.
So when you take 1, you subtract, you do 1 minus the a slice, like 8
Right,
times.
because, okay, so this 8 slice is the white area. But we had to find a shaded area, which is 1 minus that, because the area of the square is 1.
I see. And then 8, is that 8 times a slice, which is
This pink thing, how many pink thing makes up the white one? 1, 2, 3, 4, 5, 6, 7, 8.
8. Oh, okay, so that's
See,
what, okay.
that's what we computed here. That little. So 8 of them makes up the white region. I'll try to remember it. It's a really cool problem. think they're asking for an angle of for an area, but it's. So we start with a square, and then there is a quarter of a circle, and there is a semicircle, I think, like this. And now, yeah, how big is this? So that's a little messier. So I can show you the other application. So Havana, Cuba, and Tampa, Florida have approximately the same longitude. The latitude of Tampa is 28 north, and that of Havana is 23.1 north. There is the radius of Earth. Find the distance to the nearest mile between the two cities. This is a very simple math problem. It's the geography and the convention of what the hell does that latitude mean that I have to explain. It's not the math. What do you get when you take a plane and you slice into a sphere? You slice a sphere with a plane, what do you get?
You get a semisphere.
No, oh, a cross section. So what you're answering is, your answer is, let's say, correct. But what I meant is, here is a sphere and you cut a plane through it. And then what points of the sphere are on this plane? And what I was trying to get at you is that no matter how the plane is, it's always a circle. You can, so this is a circle. I know it looks like an ellipse. This is a bad picture, but try to actually imagine a sphere in front of you and you cut a vertical, it's like a melon, but more spherical. And you cut it into two parts, and then you look at the two parts. The top is supposed to a circle. The top is gonna fall. So the two things, you cut the melon into two things, both of those will have a circular top. That's what I'm saying. So no matter how you cut a sphere, it's always by a plane, it's always a circle, the cross section. Semi-sphere, you have to go at the equator, but basically you're right. So here is the Earth, and being on the same longitude means that if you go from North Pole towards the South Pole, you're gonna hit the two cities on the same line. This is the center of the Earth. This is the North Pole. I'm not sure I'm helping here. And this is the equator. I'll try one more. So this is the equator. This is the center of the Earth. We go out to the equator, then we go up to the North Pole. I messed it up. And so let's say we rotate the sphere so that here are the two cities. We just rotate it until you see it's just a little bit of an arc length between the two cities. And then that other numbers, they basically, what they mean is connect the center of the Earth with the equator like this. And then those two angles were given. This angle, the smaller one, was given to be 23.1 degrees. And it's north, meaning it's above the equator, not below. I think this is the actual language, terminology that is used in geography. And then this other one is, I assume that's Florida, yeah. So Havana is here, Florida is there, that's 28 degrees, also towards the north. And it was given that the radius of the Earth is 3,960 miles. Do you see that this is just a very, very basic arc length problem now?
Yep.
It's just what is the angle? So the arc length of a circle, the circle has radius 3,960 miles. What is the angle that we have to use for this little arc subtended? What angle subtends this arc, this here?
Like the whole angle?
No,
Or
this.
just, oh, this one?
That's the
that
distance.
was
We have to
28.
find the distance between the two cities.
Isn't that 128, the arc right there? It's also
No, 128 is this arc.
oh,
You said 128? 28 is from
28.
the equator, right? It's always from the equator. 28 north means this, that this angle is 28.
Oh, the whole thing's 28. Okay.
Right. So from the equator to Tampa, Florida, this angle is 28 degrees. And for Havana, Cuba, it's more south, it's 23 degrees, 23.1 degrees. So we have to find this arc length. What angle subtends this arc? This is the distance. So the distance between two cities, it's not a straight line because we live on a sphere, it's an arc. So what is this angle here that I'm keep massaging? This
Isn't
angle
it
here.
isn't it 4.9? Like, don't you just subtract
Yeah,
two?
yeah, you do. I told you the math is not hard here. It's just translating the geographies. Yes. So the question is, what is the arc length, which is usually denoted by lowercase s? Don't ask me why. So that's arc length. If the central angle that subtends it is, if this 0.1 wouldn't be there, it would be 5. So it's 4.9 degrees. And the radius is 3960 miles. And then poof, the word problem is over. It's a very basic problem, but it scares the hell out of people at first. Hopefully that's not going to happen again. So we finished on time. You can compute. You can do the computation. You will see it on the handout and in the practice problems. So you have seen the worst. Any questions?